It's Sarah on Zoom. Right on. Let's share the screen. And this chat. I'm guessing people are running late, or maybe we're just not going to have a lot of folks the day after a test, which I totally get. All right, just be you and me and the Zoom people. Remind me of your name. Una? How do you spell that? Oh, that's right. I saw that. I saw it because I was thinking I have a cousin whose name is Una, or it's Oona. But when I saw yours, I was like, oh, I bet it's said the same way, even though it's spelled differently. Cool. Una. She's my second cousin. She was born 5 days after me. I am the oldest great grandchild by 5 days. So, people on Zoom, there's only one person in class, which is totally fine, but I will just extra encourage you on Zoom to be participatory, ask questions if you've got them. I've certainly got things to say, but as usual, if you have questions, comments, concerns, observations, you want me to look at something specifically or talk about things specifically, you should let me know. You can write it in the chat. You can send me a private message if you don't want anyone else to see it. Totally fine. And we'll see if anyone else comes in, but if they don't, it's fine. All right. So I'm going to start. It does feel weird talking to it most empty room. But let's see. So let's start. I'm going to remind you all of what we did last week on Thursday, which is we talked about the directional derivative. So I'm going to remind everybody that for function f of xy, or I could say, I suppose, yeah, f of xy. The directional derivative of the function f of xy in the direction of welcome, the vector u, is given by the following. It is the gradient of f, which is a vector, dotted with the vector u. That is very, very generally how we find a directional derivative. Now, we typically need a little more information. So I'll say, typically, we will be given the following things. We'll be given a function, f of xy. We'll also be given a point where we're actually finding the derivative at, right? Because just like functions of one variable, if someone says, find the slope of the tangent line, they have to tell you where you're finding the slope of the tangent line. It needs to be like, it could be in general, but it's not going to be a specific number if that's what they're asking. And then finally, they have to tell us a direction. So those are the three pieces of information we really need to be able to find a directional derivative. So let's look at a couple examples that are going to illustrate a couple of things. So I'm going to go back to my kind of favorite example for a minute, but then we'll do some other examples for sure. So let's look once again at our good old, I'm not going to draw the picture this time, but let's look at our downward opening paraboloid, 9 minus x squared minus y squared. And we want to find, so here's part one, we want to find so we can say slope or derivative and kind of mean the same thing. So I want to say, find the slope of this function of f of xy at the point, say, I don't know, 2, -1 in the direction of, let's go with the vector, I don't know, let's say 3, 1. And I don't remember which way. Is there a specific way you're writing vectors in class? No? Okay. So you can say 3, 1, or 3, 1, or 3i plus 1j. Right? All those are good ways of writing the vector. I'll probably most often do this. This is kind of my preferred choice, is writing it as a column for me. But if you find that your professor is using a specific notation for vectors, let me know and I will change it to that. Okay, so here's the thing about this. We have to find the gradient, we have to plug in the point, and then we have to find the direction. But the direction is a little more specific than you might be aware of. So let's see, our gradient here is not too terrible. The gradient of f is just the vector of partial derivatives. So the gradient of f is just del f del x in the first coordinate, del f del y in the second coordinate. So whenever someone says the word gradient, well, there's a couple things I want you to think, but for now, what I really want you to think of when someone says gradient is it's a vector, and it's just the vector of partial derivatives. So in this case, it's going to be the vector negative 2x, negative 2y. Great, not terrible at all. It's taking those partial derivatives. And then we're going to plug in the point. So the gradient evaluated at the point 2, negative 1 is going to be, well, I'm just plugging in 2 for x and negative 1 for y. So I'm going to get negative 4, positive 2. Okay. And then we have to dot that with the direction vector. Now, here's the thing. When someone says direction vector, even if they don't mean it, they do mean it should be a unit vector. So if I say I want the vector pointing in that direction, the problem is there's literally an infinite number of vectors that point in that direction. It could be a vector this long, or this long, or this long, right? Vectors of lots of different lengths point in the same direction. So to ensure that we're kind of all uniform in the way we respond, we're going to decide that, well, we're all going to say that if we talk about a direction vector, we're going to mean a vector of length or magnitude 1. So whenever you have a direction and the vector doesn't have a length of 1, we're going to turn it into a vector with length of 1. So I'm going to take this vector, where'd it go here? 3, 1, I'm going to call v. So v is equal to 3, 1, and I'm going to do what's called normalizing or unitizing, which is I'm going to say u, the unit vector, right? We often use the letter u for unit vector. This means a vector of length 1. We're just going to take the vector v and divide it by its own magnitude or its own length, which is just the square root of the squares of its components added together. Just as a reminder, right? When you want to find the length of a vector, you just take each component, square it, add together the square root. It's like the distance formula. It's literally the distance formula. So then we're going to get 1 over the square root of 10 times the vector 3, 1. Or if you prefer, you could write it as 3 over root 10, 1 to the root 10. There is no real need to rationalize these things. I would just leave it like this. I will point out, if you found the length of this new vector, it would have a length of 1. So just to be super duper extra clear, right? If this is my vector u, it is in fact true that the magnitude of u is the square root of 3 over root 10 squared plus 1 over root 10 squared. You kind of see that maybe. Let me zoom in a little bit here. Which is just going to equal square root of 9/10 plus 1/10, which is exactly the square root of 1, which is 1. So that is always the effect of dividing a vector by its own length. You get a new vector pointing in the same direction, but that has a length of 1. Okay, so now we're almost there. All we have to do at this point to find the gradient, to find the directional derivative, is take our gradient evaluated at the point and dot it with this new unit vector. So our actual directional derivative, and here's how this is written. The directional derivative is written as capital D subscript U F, like that. That's how it's always done. And it's going to equal exactly the gradient we just found, evaluated at our point, dotted with the unit vector direction. That's going to equal, let's see, -4, 2 dotted with 3 root 10, or 1 root 10. Sorry, 3 over root 10, 1 over root 10. And then we're going to do it. So it's like -4 times 3 is -12 over the square root of 10. 2 times 1 is 2 over the square root of 10. And adding this together, you get -10 over the square root of 10. And normally I might not take the steps to rationalize that, but specifically here, since I have 10 divided by its own square root, I might as well say, oh, 10 divided by the square root of 10 is the square root of 10. So that's going to equal -√10. So here's what this means. This means if we're sitting on the mountain, so okay, I'll try and draw the picture here. See how good a job I do. If we're sitting on our mountain, there's the origin right there. And we go over to the point where, what did I say? Where x is 2 and y is -1. So we go 2 out towards you and one to the left. So if we're kind of right there in the xy plane, and then we go up to that, part on the point there. What we're saying is if from that point we move in the direction that is 3 in the x direction, so 3 towards you, and 1 in the y direction, so 1 to the right. So kind of moving in a, okay, help me out here. Kind of going like this way, kind of going like that way, still in that level plane. If I travel kind of that way out at you, the slope of the surface in that direction is -√10. Which makes some amount of sense because if you think if we're going outwards that way, we're definitely going down the mountain. So the slope should be negative. Questions or thoughts about what's going on here?
A quick summary of like all the steps?
Yes. Fine. Let's actually so let's do another one where we'll do it much kind of faster. So paper. So let's look at this next example. Where did I go? So let's say this was our function. The function f of xy is equal to 5xy squared minus 4x squared y. And we want to find the directional derivative of f of xy at the point. Sure, let's make it a little more interesting. Let's go 3, 2 in the direction of v equal to sure -5, 12. Okay, so here are the steps. Step 1, find the gradient. I suppose you could make this in, so -10 to the 1/2 and negative square root of 10 is the slope. Yes, that's correct. So step 1, find the gradient. So here our gradient is going to be the partial with respect to x. And it's totally cool to write just del f del x del f del y first to remind you what it is. And then say, okay, that's going to be del f del x is going to be 5y squared minus 8xy. And del f del y is going to be 10xy minus 4x squared. And kind of along with that is step 2. And step 2, plug in your point. Plug in the point we are at. In this case, we're going to plug in the point 3, 2. So there's your gradient in general. So this is kind of like It's kind of like how the gradient is the derivative anywhere, and the gradient at that specific point is the slope of the tangent line at your particular point. So the gradient evaluated at 3, 2, I'm just plugging in 3 for x and 2 for y. So I'm going to get 5 times 2 squared minus 8 times 3 times 2. And then in the second coordinate, 10 times 3 times 2 minus 4 times 3 squared. And simplifying that, let's see, 5 times 4 is 20. 8 times 3 times 2 is 48. So I have 20 minus 48, which is negative 28. And 10 times 3 times 2 is 60. 4 times 9 is 36. So 60 minus 36 is 24. Okay. Then we also need to find the direction vector. Now, find is probably not the best word, because usually you're given the direction. So I would say it is perfectly reasonable to say that the direction we are traveling in is the direction of negative 512. The problem is it's not a unit vector. So what I really mean by finding the direction vector is whatever your vector is, take your direction vector and make it a unit vector. So u is going to be the magnitude, sorry, it's going to be the vector v divided by its own magnitude. Sometimes they do give it to you as a unit vector. Here's the thing though. Let's pretend they gave us the vector. Let's say they gave us the vector v equals, I'm just making something up on the side here. Let's say they gave us v equals, I'm trying to think something good here. Sure. 3 over, sorry, my brain is not working right here. 3 over the square root of 58, comma 7 over the square root of 58. Is that a unit vector? Maybe. But so here's the thing, right? Whether or not that's a unit vector, dividing it by its own magnitude will make it a unit vector if it's not already a unit vector. And if it's already a unit vector, it won't change it because it'll just be divided by 1. So if you already know it's a unit vector, yeah, totally, go right on. But if you don't explicitly know it is, you either want to check it is, and this is a unit vector, right? If you square both of those things and add them together, it will equal 1. Because you get 9 over 58 plus 49 over 58, which adds up to 58 over 58. But if you don't immediately recognize it, you can always divide by the magnitude. Here, we're going to get, in this case, we're going to have v, which is the vector. So instead of doing v divided by its magnitude, I prefer to do 1 over the magnitude. Like, I just don't like writing the vector divided by a number. So I'm going to say it's going to be the vector v, which is negative 512. And then here we are dividing or multiplying by 1 over the magnitude. That's be 1 over the square root of 25 plus 144. Which happens to be 13. 25 plus 144 is 169. Square root of 169 is 13. A lot of, no, I should say, some of the time they're going to give you numbers that are going to turn out nice. So here, this happens to be, oh, that was step 3, by the way. 1 over 13, negative 512. Okay, we've got all the pieces. Now we have to put them all together. So then finally, the last thing we're going to do is we're going to say that, all right, the directional derivative of f in the direction of u is just going to equal the gradient of f evaluated at our point dotted with the directional derivative u. Sorry, not the unit vector. All right. And so in this particular example, we're going to get that the directional derivative is equal to our gradient. So negative 28, 24, which are not the best numbers ever, dotted with the unit vector 1/13 times the vector negative 512. In this particular case, so this is why I kind of like having the 1/13 on the front. I'm just going to ignore that until the very end. I'm going to say that that's equal to 1/13 times whatever the dot product is. So I'm going to get negative 28 times negative 5 plus 24 times 12. Which is, again, not super lovely, but it's equal to 1/13 times negative 28 times negative 5. Here's a cool trick about multiplying by 5. Instead of multiplying by 5, multiply by 10 and then divide by 2. So 28 times 10 is 280, divided by 2 is 140, which is definitely 28 times 5, 140. I like that trick. It's a good trick. 24 times 12 is a little bit harder, but I see that 24 is 2 times 12. So I have 2 times 12 times 12, and 12 times 12 is 144, and 2 times that is 288. So I've got 140 plus 288. So I end up with a very large number, 428 over 13. Which, unless that happens to go into it perfectly, which it doesn't, I would just leave it as is. Although it's very close. Yeah, it's like 1 off. If it was 429 over 13, it would totally perfectly be, I think, equal to 33. Anyway, oh, you can't see that, sorry. So, what this means, again, just for the physical interpretation, what this means is that at this point on this surface, if we move in this direction, the slope of the surface is this wildly large number. Right, definitely a positive. So definitely, if your directional derivative is positive, it means you are going up the surface. Where if it's negative, it means you're going down the surface. And kind of an interesting thing about these three-dimensional surfaces is as long as they're not like super duper weird, like in discontinuous stuff, there's always a direction where the derivative will be positive, and there's always a direction literally turn around and go the other way that the derivative will be negative. It's kind of neat. Okay, let me give you, so let me ask you a slightly different question, but I'm still, let's use the same one here. What if instead I said, all right, so here's another way of phrasing this question that asks you to do something just a tiny bit different. It's still mostly the same. So I'm going to still look at the same function. So I still have f of xy equal to 5xy squared minus 4x squared y. And now I want to find still the directional derivative of this function, f of xy, at the point 3, 2. Now be careful here. Watch what I write next, because it's going to be slightly different. In the direction of, let's say it's going to be that. Let's say it's going to be, I don't know, 7 comma, do I want to make it really easy? Sure. 7 comma 6. That's not easy, James. 7 comma 5. Now I'm going to make this a little bit more explicit here in the direction of the point 7 comma 5. I've definitely written that as a point, not as a vector. So here's what I mean by this. Our direction isn't the vector 7, 5. We're not moving in the direction of going over 7 and up 5. What we're doing is we are starting at the point 3 comma 2, right? Because we're finding the directional derivative at the point 3 comma 2. And from that point, we're moving in the direction of the other point 7 comma 5. So our direction is actually whatever it takes to get from there to there. What's the actual vector from 3, 2 to 7, 5? Well, how much over do I have to go to get from 3 to 7? And how much up do I have to go? Right. So just as a word of warning, sometimes they will phrase the question where they say in the direction of the vector, and then the vector is just your direction. Sometimes they'll say in the direction of this other point, and then you have to find the vector from your beginning point to your end point. So just be careful, because I've definitely seen both phrasings in web work. So to do this one, it's the same sort of work. And I should say, it's so much the same work that I shouldn't repeat myself, in that we should definitely say, I don't need to do the work of finding the gradient again. The gradient's still the same. So let's just write that down. The gradient here is still 5y squared minus 8xy. And then the second coordinate is, or second component is 10xy minus 4x squared. And specifically, the gradient evaluated at 3, 2 is still negative 28, 24. But now our unit vector has changed. Our unit vector here is going to be the vector v divided by the magnitude of v, which in this case is going to be the vector 4, 3. And this is kind of a classic example when you have that vector. What's the magnitude of the vector 4, 3? Or what's the hypotenuse of a 3, 4 blank triangle? Anybody? Let me draw a picture. If I drew this right triangle, said this side was 4 and this side was 3, you would tell me that the other side was how much? On the Zoom. I'll give you a moment. I know you all know it. So what's it going to be? Yeah. So here's the thing. And then you can totally do it like the normal way. And then you can just say, oh, yeah, I know the magnitude of v is just the square root of 4 squared plus 3 squared, which is the square root of 25, which is 5. But I just want to mention that you'll often see vector, like people use this example a lot. They'll give you the vector that's 4, 3, or negative 3, 4, or 3 net, right? They'll give you something where one component's plus or minus 3, the other component's plus or minus 4, and they'll just kind of jump to saying, oh yeah, we know the magnitude is 5, because it's really coming from a 3, 4, 5 triangle. So here our magnitude is 1/5, or I should say our magnitude is 5, and we're dividing by that 5. So here, now we can calculate the directional derivative, and it's going to equal the gradient, which was negative 28, 24, dotted with the unit vector 1/5. And then we just do the same sort of work. So it's going to be, I like to factor out the 1/5 and say we're going to get negative 28 times 4 plus 3 times 24. Which is something. Okay, fine. It's 1/5 times 28 times 4 is 112. 3 times 24 is 72. So negative 112 plus 72 is negative 40. So you get 1/5 times negative 40, which is negative 8. So from the same point, if we change the direction we're going in, now our slope is negative 8. That's a positive, super big number. Okay. Ow. See here, I want to check out one thing here. Okay. So I didn't say that, sorry, I might have misspoke. The direction is not negative. In fact, there aren't any really, what's up? This is not, are you looking for Casey? Yeah, I think you didn't do that revolving door. So if we are on a slope no problem. So if we are on a surface, right, there isn't really a positive or negative direction of travel. Unlike, I would say, unlike like in the normal like XY plane, typically we think of going like to the right as being in the positive direction, to the left as being in the negative. But here we don't really have that. Instead, what I should have said is that at this point, 3, 2, the directional derivative is negative. Oh, sorry, I'm putting the wrong thing. Is negative in this direction. So what we're saying is the slope is negative. Meaning if I travel in this direction, on the surface, I will be going down the mountain instead of up the mountain. So I would strongly encourage you to think about like when you're finding these directional derivatives, the idea is kind of you're on a surface, you're out hiking in the mountains. And if your directional derivative is positive, you are going up the hill, up the mountain, up the slope, whatever. Your directional derivative is negative, you're going down. And if your directional derivative is 0, it means you're on like a nice level curve and you're not changing your elevation. which is the nice, like, that's what we like to do around hiking. Like, you don't want to go super up or super down. Let's see. Oh, that's a good question. I should definitely get to that at some point. So let's look at a couple more examples here. So I've got some more notes here I want to grab. Not grab those notes. Okay, well, we'll get there in a second. So, excuse me. So you all try this one. So first, I want you all to, things in order here. I would like for everybody to find the gradient of the following. Find the gradient, which is a vector of f of x, y equal to, what do we got here? X squared times y cubed. Go ahead and find that gradient. It's not too terrible. A few seconds. So for the first component, we should be getting 2x times y cubed. The second component, we should be getting x squared times 3y squared. Taking those partial derivatives. All right, now I want you to find the directional derivative of this function f of xy equal to x squared times y cubed at the point -2, 2 in the direction. I'm going to make it kind of not pretty here. In the direction. Sure. 4, 1. So I want you to do all the things. Go. Give you like a minute and a half. I think about my next moves here. These are like walk around and look, but I feel like I think the first component should be -32 for the gradient, but not -48. But the work looks mostly good. So let's take a look and see. If I take my gradient, plug in -2 for x and +2 for y, I should get 2 times -2 times 2 cubed, which is -4 times 8, which is -32. And then for -2 squared times 3 times 2 squared, I've got 4 times 3 times 4, which is 4 times 12, which is 48. Kind of gross numbers, but such is life. So then if I was calculating this, I would just go straight ahead and say, okay, great, I'm going to get -32 comma 48 dotted with calculating what the unit vector u is really straightforward. Just take your v, which you've already got, and what am I dividing by? What's the magnitude of that vector? So what? There's something else though. There's a yeah, the square root of 17. Exactly. Which is always like, I will be honest, that kind of part's almost an afterthought. Like it's important, no doubt, but you don't really do anything with it other than just at the very end say, great, divided by that. So I'm going to do the dot product first, which is going to be -32 times 4 plus 48 times 1, all divided by the square root of 17, which is, I don't know, -128 plus 48, which is -80 over the square root of 17. And that's what it is. I don't really care about getting a decimal approximation, although we totally could. Okay. So now let's ask an interesting question here. Yeah. So here is an interesting question that's going to help us think about some other stuff. So for this function, for f of x, y equal to x squared times y cubed. I'm going to pick a different point to make this question interesting. So we'll do two things here. First, I want to find the directional derivative. I knew there was a reason I shouldn't have changed the point. At the point. Yeah, that's fine. It's good practice. At the point, what do we got here? 2, -1. In the direction of another point. What we got here? Q of 60 of the point Q, which is 6, 2. So let me ask you all. My vector, so like when I say this in the direction of Q 6, 2, what I'm really saying is my vector V is what? There's actually an easy way to calculate it. If you're starting at this point here and ending at that point there, it's just this x minus that x and this y minus that y. So it's going to be 6 minus 2, 2 minus -1, which is 4, 3. Whose magnitude is what? It's a 3, 4 triangle. Yeah, exactly. So right when you see a 4, 3 or a 3, 4 or a -3, 4 or whatever, like you know it's going to have a magnitude of 5. Okay, great. So let's find the directional derivative real quick. I'll find the directional derivative maybe. Gradient hasn't changed from last time. Well, I should say that's not entirely true. The gradient as a function hasn't changed, but the gradient at the particular point has because we picked a new point. So the gradient is still what it was before, 2xy cubed, 3x squared y squared. But the gradient at the particular point, so sometimes people write it like gradient of f evaluated at 2, -1. Sometimes people write it as gradient of f evaluated at 2, -1. Just be aware of different possible notations for writing this. Either way, when I plug that in, I'm going to get 2 times 2 times -1 cubed, and then I'm going to get 3 times 2 squared times y squared, which is -1 squared. So I end up getting a gradient of 2 times 2 times -1 and 3 times 4 times 1. So that's my gradients. Interesting. Okay. So now, oh, and then we should find the directional derivative. So the directional derivative is going to be my gradient, which is going to be negative 412, dotted with my directional derivative, which we know is dotted with my direction vector, not my directional derivative. So dotted with the direction vector, which is going to be v, the vector 4, 3, divided by its own magnitude, which we already said was 1, which was 5. I'm dividing by 5, I'm multiplying by 1/5. And so let's see, calculating this, we get negative 4 times 4 plus 12 times 3 times 1/5, which is 20 over 5, which is 4. So that means at that point in that direction, you're going up the hill at a slope of 4, meaning for basically for every like 1 foot you traverse horizontally, you end up going 4 feet up further in that direction, at least at that particular. So now here's the interesting question I really wanted to get to, which is the following. Is there a direction in which the directional derivative is equal to 13? And this question gets at the heart of a lot of things here. So, paper. So it might feel like the answer is unknowable, but it's definitely knowable. So here's how we go about this. Let's talk about the directional derivative more generally for a second. We'll come back to this. So directional derivative is equal to the dot product of the gradient of f with the direction vector u. Now, here's what I want you to remember. Normally, we calculate this dot product in the easy way. First component times first component plus second component times second component, right? It's just the straightforward, like, thing times thing plus thing times thing. But there's another way of calculating the dot product between two vectors. And I'll remind you that the other way is taking the magnitude of the first vector times the magnitude of the second vector and multiplying by cosine of the angle between them. So just as a reminder, if your gradient vector looks like this, and the direction you're going in vector looks like this with a length of 1, and that's the angle between them, then you could totally calculate the dot product between the two vectors by saying it's this length times cosine of that angle. And here's why this is important. One of these things we know, and one of these things we can bound. What's the magnitude of the unit vector u? How long is a unit vector? 1. So this is equal to the magnitude of the gradient times 1. And no matter what, whenever you take cosine of an angle, what's the biggest you can ever get when you take cosine of theta? Also 1. So this is definitely less than or equal to the magnitude of the gradient. Let's say that again. The directional derivative at the most can only ever be equal to the magnitude of the gradient. So that's actually an important thing. Let's write it down. So the maximum value for a directional derivative is the magnitude of the gradient at that point. And there is definitely at least a couple homework problems that ask you to find the maximal value, or ask you to find the maximal value of a directional derivative. And it is always the magnitude of the gradient. So let's go back to the question before we explore this a little bit more. We go back to this question over here. Is there a direction in which the directional derivative is equal to 13? The question they're really asking us is there a place, can the directional derivative ever be as big as 13? So if I take my gradient Here's my gradient at the point. My gradient at 2, -1 was equal to -4, 12. And if I take the magnitude of that, it's equal to the square root of -4 squared plus 12 squared, which is equal to the square root of 16 plus 144, which is equal to the square root of 160, which is not quite 13. 13 is the square root of 169. So this is definitely strictly less than 13. So the answer is big old no. Because no matter what direction we point in, the steepest slope we can get is the square root of 160. This is not 13. So, a couple interesting things to make note of here. Back in the other thing. The maximum value for a directional derivative is the magnitude of the gradient. So, just kind of looking over here for a second. Like, for example, in problem 8 of your homework that's due on the 19th, the question says, find the maximum rate of change of f of st equal to t e to the st at the point 0, 4. So they're asking you to find the maximal rate of change at that point. All they're asking you really to do is to find the magnitude of the gradient. The magnitude of the gradient is the maximal rate of change, or the maximal value of the directional derivative. Yes. And then here's what's lovely about the minimum value. If you know the maximum, you know the minimum. Because here's what's very different about functions of 2 variables versus functions of 1 variable. If you had a function of 1 variable, right, you could be like, okay, function of 1 variable, right? I want to find a function of 1 variable like this. There's a maximum, there's a minimum. They're totally unrelated to each other. On the other hand, if you're on a surface, yeah, I'm not gonna. I'm gonna try and draw this. It's not gonna work. Well, we're just gonna say words. If you're on a surface at a particular point on a surface, and someone says, "Okay, you're at this point. What direction is the steepest?" Well, if I'm trying to make it the most positively steep, I'm saying, "What direction do you need to go in?" So then going up the most, right? Or if I'm trying to get to the top of that. So that's the maximum. And the way you find the minimum is by turning around. Because if that direction is the steepest up, the opposite direction is the steepest down. So it's actually really, really excellent that, in fact, let's write it down. The minimum value for a directional derivative, or as they phrase it over here, okay, sure. You could also say, or the minimum rate of change of your function at a particular point is the negative of the magnitude of the gradient. The negative, or the opposite of the magnitude of the gradient. Cool. This is something that took me a long time to get stuck in my head. Like, it really, when I learned this stuff, when I took, I guess 21C or 21D, yeah, whenever I took math way back in here, it was really hard for me to remember that the gradient had this property. I don't know why, it just didn't want to stick in my head, but it is really true that, and I kind of always go back to this. The reason the magnitude of the gradient is the biggest thing is because the dot product says so. The directional derivative says it's a dot product. It's going to be the biggest when theta is 0 degrees and cosine of 0 is equal to 1. but it can't ever be any bigger than that. So you can't ever get anything bigger than this. In fact, that's actually something we should mention as well. So there's two kinds of things. There's two kinds of things people like to talk about here. It's talk about what is the maximum value of the directional derivative. Okay, what's the maximum rate of change of this function? And the other thing people like to ask is, in what direction do we get the maximum rate of change? And the direction is whatever direction is steepest. So let me ask you. What direction you will maximize this? Okay, so I'll remind you, again, this is not what we usually do as far as like how we calculate dot products. Let me remind you, you've got the gradient of f pointing some direction and the directional part of the derivative pointing another direction. Theta is the angle between them. So if I want to make this quantity as large as possible, well, the magnitude of that isn't changing. It is what it is. The magnitude of u is just 1. It's definitely not changing. It is what it is. The only thing that has a kind of a variability in this equation is cosine of theta. So what we've already said it once, let's say it again. What's the biggest cosine of theta can be? 1, right? And what's the angle? I think I didn't quite hear. I think you said 1, but did you say 1? Yeah. Okay. What's the angle that theta has to be so the cosine of that angle is equal to 1? It's 0. So here's what that means. It means for this to be as big as possible, we need theta, the angle between these two vectors, to be 0 degrees or 0 radians. What does that mean, really? It means that the vectors are going to be pointing in the same exact direction. So really, the whole answer here is that to maximize the directional derivative, to can I spell? Yes. To maximize this directional derivative, we need u, the direction that we're pointing in, to point in the same direction as the gradient. Or in other words, the direction that maximizes the rate of change of f of xy is the gradient of f divided by the magnitude of the gradient of f, because we want it to be a unit vector. Let's look at some examples. But this is really here are some things I would say that are a little bit maybe shaky. If someone said what direction is going to give you the maximum derivative or the maximum slope, I would say the direction of the gradient. Now, technically that might not be the perfectly right answer because I haven't normalized my vector. But when people say directions, like when people say vectors as directions, we all are cool with saying the fact that, I don't know, everyone's usually perfectly fine with saying, yeah, these two vectors point in the same direction. 4, 2, and 2, 1 both go over some amount and up some amount, right? 4, 2 over 4 up 2, 2, 1 over 2 up 1. Those both pointing in that direction. It just depends on how you want it. Now, neither of them are the actual direction vector, because neither of them are unit vectors. But people kind of get lackadaisical about being super specific about what the vector is. So typically when people say what direction are we going to increase the fastest, the answer is always, oh yeah, it's the direction of the gradient, because the gradient is going to cross the level curves the most quickly. Remember, the level curves are the different heights. In fact, the gradient is perpendicular to the level curves. Kind of neat. Which makes sense, right? If you're trying to get up as fast as possible, even though like in the real world, you wouldn't try and like climb up the cliff, right? If you're trying to go up as fast as possible, you want to cross those level curves as quickly as possible, perpendicularly. So let's look at. Right, but related, but definitely, yeah. So let's actually look, that's a good question. Let's explore that. So here's a good question for, let's say we got the function f of xy equal to y squared over x. We want to find the maximum rate of change at the point, right? You have to be given a point. You can't just find the maximum rate of change anywhere. You have to be specific. So find the maximum rate of change at the point 2, 4, and also find the direction in which it occurs. So we're going to do this kind of the short and the fast way. I mean, the short and the long way. We'll do it the fast way first, though. So first, question 1. I know that for all this, I'm going to need the gradient. So let's find the gradient. So the gradient's going to be, it might help to write this function as y squared times x to the negative first. Make my life a little bit easier. So my gradient's going to be the partial with respect to x, partial with respect to y, which is going to be, let's see here, partial with respect to x is going to be negative y squared x to the negative second. With respect to y, it's going to be 2y x to the minus first. And I might rewrite it so I don't have negative powers, because I feel like negative powers are hard to actually evaluate. So I'm going to write this as negative y squared over x squared, comma 2y over x. And if I plug in my point, I get that my gradient evaluated at 2, 4 is going to equal negative 16 over 4, which is negative 4, and 8 over 2, which is positive 4. So there's my gradient. And if it were me, I would be like, well, that's my direction, right? The direction is 4 to the left and 4 up. But really, I should be more precise and I should normalize that vector to answer the second part of the question. But let's answer the first part. So part 1, the answer is that the max rate of change is the magnitude of our gradient, which is the square root of negative 4 squared plus 4 squared, which is the square root of 16 plus 16, which is the square root of 32. Or if you prefer, 4 root 2. So that is our maximum rate of change. Also, as a quick aside, the minimum rate of change would be negative 4 root 2. Because you just turn around and go the other direction. It's kind of interesting to think about, right? Like if your steepest up direction is one way, you can't get a more steep down direction, right? Because if you could turn towards that, and like, right, you could always be opposite of that. So you can't have an up direction more steep than your down direction. I should say you can if you have weirdly discontinuous, not differentiable functions. Like if you had something that was jagged, like was nice and smooth and then pointy, that would be a way you could have something like that. But typically we don't have that on surfaces. And the second part here is we've almost already got the answer to the second part. By finding both the gradient and its magnitude, we can almost directly answer the last part of the question, which is that the direction in which it occurs is the gradient itself divided by its own magnitude, which is equal to negative 4, 4 divided by 4 root 2, or multiplied by 1 over 4 root 2. Or in other words, it's negative 4 over 4 root 2, 4 over 4 root 2, which I would reduce to negative 1 over root 2, 1 over root 2. So when you talk about a dot product between two vectors, you're kind of asking, it's not quite exactly, but it's kind of like asking how much of this vector is in the direction of the other vector. And so you end up maximizing that when the vectors both point in the same direction. Because you're saying, oh, if they point in the same direction, then all of this one is in the direction of the other one and vice versa. So that's why having the vectors, both the direction vector and the gradient point in the same direction ends up maximizing the value. We could also do this the longer way, although it almost feels super repetitive. If we start saying, well, I know the gradient has a direction of negative 1 over root 2, 1 over root 2. If I want to actually find the directional derivative the long way, look at what happens. So if I instead say, okay, u is equal to this, and I want to find the directional derivative of f in the direction of u, well, look what happens. I get, well, again, I can do it the long way. I get essentially the gradient of f dotted with u. But the gradient of f, or sorry, I should say u is just that. What happens when I dot a vector with itself? That's a good question. Let's take a look. If I have the vector v equal to 1, 4, and I dot v with itself, I end up with 1, 4 dot 1, 4, which is equal to 1 times 1 plus 4 times 4, which is equal to 17. And it kind of looks like the magnitude formula, but what am I missing? I'm missing the square root. And actually, that's exactly what it is. This is exactly the magnitude of v, but I'm missing the square root. Just the magnitude squared. That's exactly what we have here. The gradient of f dotted with the gradient of f. If I bring out this for a second, if I bring out the magnitude, I just have the gradient of f dotted with itself. But we just said if you dot a vector with itself, you get its magnitude squared. So I really have 1 over the magnitude times the magnitude squared. And one of those is going to cancel, and we're just left with the magnitude. So that's what's really happening when you are taking the directional derivative in the direction of the gradient. You're ending up just getting that the derivative is in fact the magnitude of the gradient. So it really, really, really is true that the direction of the gradient is the direction where you get the maximal increase, and the maximal increase is the magnitude of the gradient. Okay. So, questions? You guys are asking good. You guys are asking good questions. Thank you. I appreciate the good questions. Also on Zoom, yeah. Sure. Let's see. Let me look at let me see if there's anything really spicy from the homework there. Oh, I remember there's something I want to show you that is kind of cool. Let me think for just 1 second. I know there's a thing I want to show you. Sure, I know what it is. So let me give you an example of something that's kind of terrible you might not run into, but I'm going to tell you. So let's do another directional derivative, and then we'll talk about a couple things. So I want to find the directional derivative of, excuse me, f of xy equal to, yeah, let's do something. It's kind of terrible, James. You should not do that. Let's just do this nice, not terrible one. e to the 4x times, yeah, cosine of 6y at the point 0, comma, oh, not 0. Oh, yeah, that's fine. Yeah, that's fine. That's a fine point. In the direction of, here's where things are going to get terrible. Someone did some work and found this awful, sure, 2/7, comma, 3/7. That's my not unit vector. For sure, not a unit vector. Okay. So there's something about this last part that might seem kind of terrible, but it's not going to be terrible, I promise you. So let's do the work. Let's find the gradient. Gradient, gradient, partial with respect to x, partial with respect to y. We're going to get something not too terrible. Partial with respect to x is going to be 4e to the 4x times cosine of 6y. Partial with respect to y is going to be e to the 4x times negative sine of 6y times 6. Not too bad. And if we plug in 0, 1, we're going to get 4 times e to the 0 times cosine of 0. And then the bottom is going to be even nicer. It's going to be e to the 0 times sine of 0, which is 0, and then it's just 0. So our gradient is the vector 4, 0. Quick question, easy question maybe. What's the magnitude of the gradient? What's the length of the vector 4, 0? Zoom folks, what's the length of the vector 4, 0? Type it in the chat. Yeah, it's 4. Right? If one of the components, or I should say, if all components except for 1 are 0, then the magnitude is just the absolute value of whatever non-zero component is. Because essentially you've gone over 4, you haven't gone up at all, so you don't have to use the Pythagorean theorem. All right, so now here's the deal. We need to dot that with our vector u. So we need to take, right, to find the gradient of f, to find the, not the gradient of, to find the directional derivative of f in the direction of u, I need to find the gradient of f dotted with v divided by the magnitude of v. I really would prefer not to find the square root of 2/7 squared plus 3/7 squared. That sounds terrible. Here's the thing. Here's what I really want you to do. The whole point of this example is really to show you this one little thing that I think is worthwhile. Okay, let me draw this picture here. So the vector v goes over 2/7 and up 3/7. So maybe there's a 7th, there's a 7th, 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 7th. So here's my vector v. Okay, but here's what I want to show you. You don't have to normalize that vector to find the unit vector in the same direction. You can normalize any multiple of it. So instead, what I'm going to do, and I'm going to encourage you to do, if you ever have a terrible vector that you want to normalize, turn into a unit vector, is multiply by something convenient. I'm going to multiply this by 7. So here's 7v equal to the vector 2, 3 in the same direction. And now here's what's great about both of these vectors. They both point in the same direction. And if you take either one of them and divide them by their own length, they'll both be unit vectors that point in the same direction. So instead of taking this vector and dividing by its magnitude, we're going to take this vector and divide by its magnitude. So our unit vector is going to be the vector 2, 3 divided by its own magnitude. And I highly recommend doing this in general. If you have some vector that's got terrible fractions as its components and you want to normalize it, just make it a nicer vector first by multiplying it by whatever non-zero number you like, and then normalize that. So here we end up getting the vector 2, 3 over the square root of 13. I do want to point out, just so that you all believe me, if you did it the other way, you'd still get the same result. So I'm going to show you, even though it sucks, it's not that bad. So if I took this vector instead, if I took the vector 2/7 comma 3/7 and normalized it, here's what you're going to get. I'm going to divide by the square root of 2/7 squared plus 3/7 squared. I'm going to get 1 over the square root of, let's see, that's going to be 4 over 49 plus 9 over 49 times the vector 2/7 comma 3/7. That's 1 over the square root of 13 over 49 times the same vector. But 13 over 49, well, the square root of 13 is the square root of 13, but the square root of 49 is 7. So I can really write this as 1 over the square root of 13 over 7, or preferably 7 over the square root of 13 times my vector. And then the 7s will cancel. And you get exactly 1 over root 13 times the vector 2 comma 3. Way more work to get to the same place, but you do get to the same place. So don't do this. Do this instead. Much, much nicer. Definitely a lesson worth learning, I think. So then to answer the question finally, our directional derivative is going to be the magnitude of f, the gradient of f, which is, where'd you go? A 4, 0, real nice and easy. Dotted with 2, 3 times 1 over root 13. And that's just going to be 8 plus 0 over the square root of 13. Okay, we'll do that. All right. So I will point out that I thought I saw a question on here that looked really, really hard. Right, 1 second. Oh yeah. Sorry, 1 second. So this question is, I would say this one we're about to do is similar in nature to question 9 on your homework, but a little bit different. But it's kind of got the same flavor to it. So here's the question. Here's what we've got. The derivative of f of xy at the point 1 comma 2 in the direction of the vector 1 comma 1, that is a vector, not a point, is 3. And the derivative of the function at the same point, in the direction of 0 comma 2, the vector 0, 2 is -5. And the question is, what is the derivative of f of x comma y at the point 1 comma 2 in the direction of -1, -2? So they're giving us a bunch of information, but notably, we don't know what the function is. So we need to do something else. So let's see what this means. Let's actually look at this first part here first. So I'm going to say, let's look at this. So the derivative of f of xy at 1 comma 2 in the direction of 1, 1 is 3. Well, great. We know how to calculate the directional derivative. What this means is the directional derivative at the point 1 comma 2 is equal to 3. But we know how to calculate the directional derivative. The directional derivative is the gradient of f at the point of interest dotted with the unit vector in the direction that we're going. So it's going to be the vector 1, 1, but normalized. So it's going to be 1, 1 divided by the magnitude of it. Okay, let's actually write this out a little bit more nicely. I'm going to write my gradient actually as a vector. So I'm going to write this as, so the gradient, remember the gradient's the partial derivatives. So that's going to be the partial with respect to x at the point 1, 2, and the partial with respect to y at the point 1, 2. Dotted with the vector 1 over root 2, 1 over root 2. So I don't know exactly what's what just yet, but I know that the partial with respect to x at 1, 2 times 1 over root 2 plus the partial with respect to y at 1, 2 times 1 over root 2 has to equal 3. Okay, well, that's not enough yet, but I have another equation. My other equation is that the derivative at the same point in a different direction is equal to -5. So using that, we can say, well, so let's actually just write it down the nice way. So using that, we're going to say the following. We're going to say that, again, the partial with respect to x at 1, 2, and the partial with respect to y at 1, 2, that vector dotted with, okay, if I'm in the direction of 0, 2, what's my unit vector in that direction? Close. That's the magnitude of it. So if I take my vector 0, 2 and divide by its magnitude, which is 2, what do we get? We get 0, 1. So if you know that you're pointing straight up, which 0, 2 does, your unit vector is just 0, 1, 1 in the up direction. If I said my direction vector was 5, 0, I know I'm pointing straight to the right, and my unit vector is just 1, because I'm pointing in the same direction, but with the length of 1. So then if we do this, that's equal to 0 plus fy of 1, 2, and that's supposed to equal -5. Oh, look, we just found the partial derivative with respect to y at 1, 2 is equal to -5. So then we can go back over here, say, hey, that's got to be -5. So then we can solve for the other thing and say, okay, well, that's -5. It's not going to be very nice, but I can say 1 over root 2 times fx at 1, 2 minus 5 equals 3. So then multiply by root 2, add 5, you get fx at 1, 2 equals, 5 plus 3 root 2. And then you can use those two pieces of information to say, okay, now I've actually got the gradient at the point. So paper. So what we can say is, great, if I want to find the derivative of this function at this point in this direction, we're going to say, okay, it's going to be that the directional derivative is equal to the gradient of f at 1, 2, which we know, dotted with the unit vector in this direction, which is going to be -1, -2 divided by the magnitude, which is the square root of -1 squared plus -2 squared, which is going to equal, so again, our gradient is, there's our really not nice fx part, 5 plus 3 root 2. Here's our slightly nicer y part, -5, dotted with this mess over here, -1, -2 over the square root of 5. And so then we can multiply it out. It's not particularly pretty, but we end up getting this times that, which is -5 minus 3 root 2, this times that, which is plus 10, all over the square root of 5. Or simplifying just a tiny bit, 5 minus 3 root 2 over root 5. So that's kind of the same nature as that problem 9 on your homework. It's definitely use the given pieces of information to write down a couple of equations where you don't actually know what the partial derivatives are equal to, but then you can use those pieces to solve for the partial derivatives and then go back and actually answer the question. It's a little complicated, but it's totally reasonable. All right, it's 3:01. You should stop. I will head over to CADS, and if you want to come see me, I will be there. See you later.